Hi, welcome to video number 122. This video is on proportion and direct or inverse. This is an introduction to direct and or inverse proportion. It does get more complicated than this, but this is the sort of grade 4 level stuff that you need to be able to understand if you're doing foundation maths. So keywords here are proportion, direct and inverse. If something is in proportion, as one thing goes up, the other thing goes up. That's what direct proportion is. Or it's as one thing goes up, the other thing goes down. And that is also referred to as being in proportion, but it's inverse proportion. All right. Now, you can think of examples in real life for any of these things. Direct proportion, the harder you work, the better your results get. Right. There's an example of direct proportion. All right. Inverse proportion is a little bit harder to think of, but you think of the more food you buy, the less money you have, or something like that. Okay, so one thing goes up, the other thing goes down. Okay. Now this is another example, I should say, of the unitary method coming in very handy, but these questions require careful consideration. Direct proportion is easier. Divide for one and then multiply for all. That's exactly the same as the unitary method video that I have spoken to you about. But inverse proportion requires you to do the exact opposite. Multiply for one and then divide for all. You just have to learn to recognize which type of question is which, and that's the tricky thing here. You also need to learn what the proportion graphs look like. So I've included that in the third question. So in number one, a machine fills 2,000 bottles in 5 hours. How long will it take to do 7,000 bottles? So let's work out how many bottles it can do in 1 hour. And that would be a useful thing to do. So bottles to hours, 2,000 to 5. All right. So if we divide by 5, we're going to get how many it can do in 1 hour. And then we're going to divide this side by 5 as well. So that divides by 5 and that divides by 5. So this is in direct proportion, this question, because as one thing goes up, so does the other thing. The amount of time goes up, and so does the number of bottles that are being filled. So that's going to be 20 divided by 5, which is 4, and then 0, 0. So 400 bottles in 1 hour. That makes sense, doesn't it? Okay, if it does 400 in 1 hour, it can do 2,000 in 5 hours. 5 hours is a longer period of time. So we need to know how many it can do, how long it's going to take to do 7,000. All right, so 7,000 there. Right, how are we going to get from 400 to 7,000? Well, let's see, and let's bring the calculator in to see what we need to do. So we're going to go 7,000 and divide it by 400. And we would need to multiply there by 17.5. So 17.5. All right, so that means that we need to multiply that by 17.5. All right, see what I've done? I've divided and then I've multiplied. All right, but I had to figure out what I needed to multiply by, so I used the method that I've shown you how to do that, and that's going to be 17.5, 17.5 hours. All right, hopefully that makes perfect sense. All right, and you could think of it in another way as well. You could think of it as 2,000 is 5 hours, so you could double that. All right, and that would be 4,000 in 10 hours. Right, and then you could think of that as 20 hours being 8,000, and that then makes sense as an answer, doesn't it, for 7,000 in 17.5 hours. All right, that's just a way that you could think about that without having to use a calculator. Now, in number 2, you've got 3 painters can do a job in 4 hours. How long will it take one painter? So this one is an inverse proportion question. All right, if 3 painters can do it in 4 hours, how long is it going to take for one painter to do it? Okay, the number of painters is coming down here. Right, so it's a case of multiplying first and then dividing. So we're going to multiply the painters by the hours, and that's going to give us how long it takes for one painter to do the job. Right, because obviously one person is going to take longer than 3 people. Right, so 3 multiplied by 4 is going to be 12 hours. All right, tricky. A lot of people make mistakes on those sorts of questions there. All right, but just think of it in just logical terms, in common sense. All right, dictates that one person is going to take longer than 3 people do. All right, so how long is it going to take 5 painters? Well, now we know how long it takes one painter. All right, we can just divide that answer. All right, and so I didn't show you what I did there. So 3 times by 4, all right, equals our 12. We're just going to do 12 now divided by 5. and that's going to give us our answer. So 12/5 of an hour, which we could work out on the calculator. Why not? 12 divided by 5, right, which is 2.4. Right, now if we wanted that in time, that makes sense, 2 hours and 24 minutes. All right, so we could write that down, 2 hours 24 minutes. All right, that or that, it's acceptable either way. All right, I quite like that though. I think that's a bit nicer, makes more sense to people. All right, now what assumption have you made? Well, the assumption in these instances is that the painters all work at the same rate. Okay, so painters all work at same rate, which in reality it's not likely, is it? All right, it's not likely you're going to get 5 people that all work at exactly the same rate. It's just not normal. Okay, there you go. So that could also have a question attached to it where it says what assumption you made and what effect does it have on your calculation. You could say it's going to make, if people work faster, the time would go down, and if people work slower, the time would go up. All right, so those are the sorts of effect it would have on your answer. All right, let's have a look at the third question then. It's going to match up the graphs with the proportionality statement. Now I'm just going to tell you which ones are which here. All right, so this graph B, all right, graph B is the one that you should recognize first off, and this is a direct proportion graph because it starts here at 0, 0. Either way you look at it, all right, it goes through the origin. Okay, and that one is direct proportion. So y is directly proportional to x. So there you go. That is graph B. All right. Now, I've shown you what an inverse proportion graph looks like in the positive quadrant before, I believe, right? Which is this. Okay. So there's that and there's that there. So it's between these two for one's inverse proportion. All right. Now, if you had everything as negative, all right, then it would be this. It would be this one here as well for the inverse. Y is inversely proportional to x. Okay, so this one is A. Okay, this one here. So we've got those two done. Now y is directly proportional to x squared. This is the graph of y equals x squared. All right, y equals something lots of x squared. So that's this one. That must be D. So BAD, and then the last one is C. Y is inversely proportional to x squared. So there's our inverse proportion graph, and there's our inversely proportional to x squared showing. That's what's going on there. All right, it's really tricky to explain. There's no need to explain it any further than what I've done, because you just have to be able to recognize different types of graphs there. Okay, and that question is never going to change. So there you go. Hope you've enjoyed that video, and hopefully you got an idea of what to look out for when to recognize these particular types of graphs. Nice little time calculation that we've done in that second question as well there. So yeah, thanks for watching, and hope you watch another one. Take care of yourselves. Bye bye.